Hello, welcome to AP Daily. My name is Dan Bonarigo, and I teach at Riverside Brookfield High School in Riverside, Illinois, just outside of Chicago. This video is on topic 1.4, identifying and correcting errors. In this video, we'll learn that errors are an inevitable part of programming, but understanding how to correct errors is essential to being a proficient programmer. So, what specifically will we learn? Well, we're going to learn how to correct the error that's in an algorithm or in a program. All right. And so we want to understand that the following are effective ways to find and correct errors: test cases, hand tracing, visualizations, debuggers, and adding extra output statements. So let's look at some examples. All right. So what do we do once we've identified an error? Well, the easiest error to correct is usually the syntax error. So most integrated development environments, or IDEs, display information when there is a syntax error. So this information usually directs the programmer to the line in the program where the error has occurred. So here's an example, right? Syntax error, bad input on line 2, right? So this says, hey, go look at line 2. Now, sometimes the user needs to do a little digging to find the error, right? Sometimes, it says line 2, but it maybe is line 1, or it's an adjacent line, right? Because I forgot to close something on a previous line or on a subsequent line or something like that. But generally speaking, the syntax errors or the programming language kind of gives you a hint, like, hey, this is where we're having a problem, right? And so the syntax error, remember, is one that causes the program to fail to run, and so it kind of directs you to try to fix it. All right. And sometimes it's just a typo, missing parentheses, quotes, curly brace, something like that. All right. But what do we do once we've identified the error? Well, the more difficult errors to find and correct are logic errors. A logic error is not always immediately noticed, right? It is sometimes very difficult to identify the logic error. So using test cases is the first strategy programmers use to find logic errors. Now, remember, a logic error is one where the program runs, right? You didn't get a syntax error. It ran or it compiled, right? But now the program is behaving unexpectedly, right? So for example, the program on the next slide can be used to display a letter grade that corresponds to a percentage, but does not work correctly due to a logic error. Well, it doesn't work correctly always. Okay, it may work sometimes. So let's take a look at this. All right, you see that this asks the user to input a grade. All right, and then we're going to ask if the grade is greater than 89, display A. If the grade is greater than 79, display B. Greater than 69, display C. Greater than 59, display D. Otherwise, display F, right? So how do we know that this program code segment does not work? Well, pause the video and think about how you would know that this doesn't work, or maybe you're unsure. So think about that. All right, so what did you come up with? Well, how would we know that it doesn't work? We should use a number of test cases, right? So if I plug in the number 95, is that going to show me it doesn't work? Yes, because it's going to display A, B, C, and D. Okay. If I plug in 82, it's going to display B, C, and D, right? But it was only supposed to display B. So I'm going to know that it doesn't work. If I plug in 76, it's once again going to display C and D, right? Which is still not what it was supposed to do. But what if I plug in 61? Well, that's going to display D and only D. So that would make me think that it does work. And if I plugged in 58, that would also display F correctly. And so that would make me think that it does work, right? So we have to use a number of test cases, right? Now, we also need to think about border cases. Well, what are border cases? Well, border cases are, where it would go from one output to another. So for instance, what's the border case for an A? Well, a 90, right, is a border case, but are we rounding up, right? So think about, like, if I had an 89.5, let's say that that should count as an A, right, if I'm rounding up, but an 89.4 should not, right? So then those values should be tested and would show that this program is not working correctly. So think about it. If I plug in 89.5 and 89.4, right, that is going to say A, right? Because I have if grade is greater than 89. So something to think about. All right. Now, how can we correct this code segment so that it accomplishes its intended purpose? All right, so go ahead, pause the video, think about how you could correct this. All right, so I have a couple of examples of how you could correct it, and there are certainly more. All right, so one way is if you took each subsequent if statement and put it inside of an else from the previous if statement, that would still accomplish the goal, right? So if grade is greater than 89, display A, right? So if you plugged in 90, that would work, and then the else would not execute, so none of the rest of the lines of code would execute, all right? And so on. Now, here's another way. Well, what if I just used and statements, right? So if grade is greater than 89, display A, but then the next one, if grade is greater than 79 and grade is less than or equal to 89, then display B, right? That would then make this code segment work as intended, right? So these are two ways, but by no means do these represent all of the different ways that the code segment could work, all right? Now, here's another example, hand tracing. Hand tracing can be most useful with iteration or with loops. All right, so hand tracing is simply writing out the values of the variables within the loop as it iterates, as it goes from one turn to the next to determine if the outcome is correct. Hand tracing can be useful for small code segments and loops that iterate a small number of times. Larger code segments or loops might require something called a debugging program. All right, so take a look at this program. Okay, now I'm using a list here. So if you haven't discussed list yet, don't really worry so much about that, but I'm using this to talk about iteration, right? So this program is intended to find the minimum number in a list. So if you look at this list, you would say, oh, okay, -3 is the minimum number. Does this program accomplish that, right? So I want you to pause the video and I want you to think about what this program would accomplish, or would it accomplish what we intended? All right, so the fact is that this code segment is intended to display the minimum number in a list, but does it work? Well, the answer is no. Let's use hand tracing to determine this. All right, so I create a table. There are 4 variables here. There's the minimum variable, there's the index variable, there's the list index, there's the list index plus 1. All right, so initially the minimum is 2, right? The first element in the list. The index is 1, right, as it was defined. All right, list index, well, that would be list at index 1, and so that would be 2. All right, list index plus 1, that would be list at index 2, that would be -3. So the first question says, if list index is less than list index plus 1, so is 2 less than 3? The answer is no, right? So minimum is the same, right? So minimum stays at 2. All right, then we increment the index by adding 1 to it, and then we repeat the next time through the loop. All right, so next, now the index is 2, so list index 2 is -3, then list index plus 1. So now we're comparing -3 to the next element, which is 5. Is -3 less than 5? Yes. So now the minimum is -3. Then we increment the index, so now we add 1, and then we start the loop again. So now the list at index 3, well, that would be 5. Is 5 going to be less than 1? All right, and the answer is no. So the minimum stays at -3. Then we increment the index to 4, and now we say, okay, is the next element in the list 1 less than the next one, 10? And that is true. So now the minimum is set to 1, right? And then the index is incremented, and then we ask, now is 10 less than 8? And no, 10 is not less than 8, so the minimum stays as 1. So the minimum is 1? That's not right. The minimum is -3 by looking at the list, right? So hand tracing showed us that the algorithm was actually just displaying the last time a number was less than the number after the if in a list. What if we used 1, 4, 0, 3, 2 as our list? Well, if you go back, you could see the algorithm would have displayed 0 as the minimum, hence the need for multiple varying test cases. Now, to correct this algorithm, we would simply need to ask if the minimum is less than the list index rather than the list index is less than the list index plus 1. And then we would need to repeat the length of the list times rather than the length of the list minus 1 times. Another strategy is by adding extra output statements, right? A programmer would use this strategy to help find and fix an error. Once the error is corrected, the extra output statements are usually removed. This has a similar effect as hand tracing, but it allows the computer to do more of the work. Now, if those strategies fail, some IDEs allow programmers to use visualizations and or debuggers. So visualizations are simply, they show graphs or images or color, etc. Things that can be visualized, right? That can help determine if a program is working correctly or not. Debuggers use software designed to run a program, allowing it to be paused and tested in the midst of running to determine if it's working properly. So what should we take away from this AP Daily video? Well, we should have an understanding of how to correct an error in an algorithm or program. And we should be able to identify some of the effective ways to find and correct errors. Thank you for joining this AP Daily video.